Okay, so like we talked about before, we're going to be adding and subtracting vectors. Now I know I've already done this part here, but when we add and subtract vectors, we take the, I'm just going to move these back. If we're adding vector A and B, we take the tail of one of the vectors and add it to the tip of the other, and we get our resultant vector, which is the beginning to the end. That's what our red line is here. And we can do it with either of them. It doesn't make a difference. We'll end up at the exact same point. Okay, so if we're adding vector AB and AC, we essentially get resultant vector AD. And in order to solve for magnitude and such, we're going to use cosine law, sine law, or SOHCAHTOA, depending on type of triangle. So, same type of triangle we had before. To make it a little simpler, we got rid of the bearings, and we're just working with the angle in between. Now, there is a very fast way to go about this. One of the things we're going to do, we're going to add these together. That means I'm going to take vector A, and move it to the tail to the tip of vector B. Okay? And what we're going to do here is we know our resultant vector is going to be from the beginning to the end. But essentially what we need to figure out is this angle in here. And there's actually a really quick way to do this. Imagine we've extended this line a little farther. So I'll do that with a dotted line. If I extend this line a little farther, hopefully that's roughly the same angle. I know it's not perfectly straight, but what angle is in here? 65, right? It's the exact same angle we had before. And since this is, though I didn't draw it perfect, supposed to be 180 degrees, these are supplementary angles, so we just have to find the other supplementary angle to 65, in this case, which is 150. So that quickly helps us find the angle in between. And we know the magnitude of A, okay? So the magnitude of A is 40 or 40 kilometers an hour, let's say, and B is 50. So using that information, we know we can use our cosine law. And I'm just going to quickly recreate that triangle again. It looks roughly something like this. Our obtuse angle in between is 115. This is our 40, and this is our 50. We want to find the magnitude of our two vectors. So this is going to be looking at just the distance of this line, where we're going to be using cosine law again. So if you guys recall, cosine law is c squared is equal to a squared plus b squared minus 2ab cos c being the large angle. And you guys have probably learned it about 3 different ways. Okay, C, we're just going to call this side here the side we're looking for, which is going to make, it doesn't matter which one, A or B. And in this case, because I've already named them A and B, yeah? Oh, yeah, sorry, I didn't put the squared there. It is squared. A squared plus B squared. Because we've named this already B, we'll call 50 our side B, and we'll call 40 our side A. Okay, C is going to be our unknown. Angle C is our 115 degrees. So we have our c squared is equal to 40 squared plus 50 squared minus 2 times 40 times 50 and cos C, because it's uppercase, refers to an angle, so it's close to 115 degrees in this case. Okay, so we're going to put this in our calculator and make sure we don't make this common error. All of these values, including the cos, are multiplied by each other. So if you're going to add these two values together, make sure that you simplify this entire process before you start the subtraction. Do not just subtract 2 times 40 times 50 from these values, otherwise you'll have made an error in the process. Okay. So let's see if we can put this all together real quickly. 40 squared is 1,600. And 50 squared, I think, is 2,500. 40 by 50 is going to be 2,000 times 2 is negative 4,000. Somebody please check those. My brain is not always as good as I hope it is. And because, so this is where the common error usually happens, like I said before, a lot of people will take 1,600 plus 2,500 and then subtract the 4,000, but that's not the case. According to BEDMAS, we actually have to take this negative 4,000 and multiply it by cos 115 before we include it with these numbers or combine it with those numbers. So our 115 cos times 4,000 negative, okay? And then I'm just going to take that value and add our other numbers. So plus 2500 plus 1600 equals, okay? That's a large number, 5,790, but that's what c squared is equal to, okay? I have to actually find the square root of this value. So I'll write it out. C squared is equal to, I don't remember that number, 5790? 5790. Whew. 5790. Anyone help me out with what the square root of that is? What is it? 56.1. Perfect. Okay. So that means the magnitude of a resultant vector is 56.1. Is that what you said?
75. I mean,
Oops, sorry.
76.
That's okay. That's why we have a whole class doing it as I do it. We can check each other. Perfect. That's great. Okay, so the magnitude of this vector is 76. And we know we're looking for the magnitude because they've given us our absolute value. When I talked about having to find the bearing direction, that's a little more in Chapter 7. I'd taken us a little farther than we had to. So that's adding. Let's talk about subtracting. I'm going to take the exact same vector combination, but let's say in this case, I would like us to find what A, the magnitude of A subtract B is in this case. Okay? Well, we can make any subtraction question an addition question with just a negative value. So I want you to actually think of this as the magnitude of vector A plus negative B. Okay? So the reason I've included this addition is because I still want you guys to think of the process of taking the tail to the tip of another. Okay? The only thing is because this is a negative B value, our vector is changing directions. The magnitude will stay the same, but the direction of this vector will be very, very different. So if we take this vector here, make it an infinite cloner, we're just going to move it. It actually changes directions. Can I flip this? I don't think I can. I'll just put an arrow at the end. Okay. So instead of going this direction, which we had before, our negative B is just going to head in the other direction, okay? So now we're going to take this A value. So I take my A value, and what ends up happening here, I'm just going to put those together. Yes. And I take my negative B, and I put its tail to the tip of the other one. So now it's going in a different direction than it had before. Remember before, for adding, we would have had a resultant vector that looked something like this. Our new resultant vector goes from here to here. Okay? So if this is our A vector, and that's our negative B vector, our resultant vector here, we'll call it vector C in this case, will just be here. So a very different resultant vector, though we can still take the same idea of adding. Okay, we just have to flip the direction of one of the vectors when it's negative. Okay with that? Great. So let's say the magnitudes are the exact same. This being 65 here, and let's put the other one back up. So this is our other one. Oh, sorry, that's the wrong one. This was the old B here. This is our old B and our A, our resultant vector now. Okay, so let's take these ideas. This B is still a value or magnitude of 50. Our A is 40. And we need to figure out, and we'll extend these to help us figure this out. We still need to figure out what our angles are going to be. Okay? We know that this one angle here is 65 degrees. Okay? Where A and B cross. Okay? And because these are opposite angles here, we also know that this will be 65 degrees. Okay? So the angle between those two will again still be 65 degrees. It hasn't changed in this case. We have two opposite angles. Okay? So because we've done that now, and if that's something that's hard to see, what I'll do is I'll just move these two down. Think of that idea like this. We've just taken this value here and this value here and moved them back the other way. Okay? That was what we got from there. So because these are opposite, using opposite angle rules, this is still 65 degrees. Okay. So now we know the angle between them. We use cosine law again to find the magnitude of vector C, or the magnitude of A minus vector B in this case. So our C again, we have our C squared, and I'm just going to write the values in this time. 40 squared plus 50 squared minus 2 times 40 times 50. But in this time, it is cos 65. So all our other values should still stay the same. 1,600, 2,500, 4,000. The only difference is we multiply by cos 65. So I'll do this all in one shot on my calculator and the square root. So 65 cos times 4,000 when it's negative gives us this value. And then we add 2,500 and add 1,600. Here's our number. And I just have to find the square root, which on my calculator I can easily find the square root of an answer, 49. Okay? So our C is 49. So the magnitude of these is 49. Where in our last answer, the magnitude was 76.1. Okay? So that's the adding. Let's go over more. There it is. That's the adding and subtracting of vectors here. What I did want to talk about is, let's say we have vector AB, okay? And we have vector, in this case, BA. Assuming these two vectors are collinear. So in other words, what I'm saying is, if this is vector A, then we go on the assumption that that is vector B, and they have the same magnitude. Okay. So all it is this is our A, this is our B, this is our A, and this is our B. So BA, arrow, BA. Assuming this is the case, we can also represent BA as the value of negative AB. Okay? So negative AB is also equal to vector BA, which means if I were to combine these vectors, AB plus BA, does anyone know what I would get as a resultant force? 0, that's right. We have a vector value, or magnitude, sorry, of 0 in this case. Okay? So that's very important. Essentially, think of like we're going up a line and coming back the exact same line, so we're back at the same starting point. So if I start at A, and I'm on vector AB, and then I add vector BA to it, we go up to the end. We go up to the end here, and then we just come right back down to the starting point. So anytime we go around a few resultant vectors and end up at the same starting point, our resultant vector will be 0. Okay? Something like that would be, I guess, a way to show it. For instance, let's say on the last question we were, here's a tougher example. Let's say I started here. I went up vector A. So if I take vector A, subtract vector B, and I'm actually going to, because I called that vector C, okay? I called this resultant vector vector C. I'm going to subtract vector C in this case. Our resultant vector here is going to be 0, because think of it like we're following a map. I went up A, back across B, and because this is positive C here, negative C would be coming back down. I'm back exactly where I started. So because I ended up back where I started, our resultant vector has no magnitude to it. It's a value of 0 in that case.